All right, we're going to start Unit 3 now. And the first thing we're going to cover in Unit 3 will be um, learning about moles. So let's say I have a Chem 122 class that has 200 students. One day I decide to bring in jelly beans, and I want each student to have 10 jelly beans. How many total jelly beans do I need to bring? Um, so my students would probably prefer me not to touch all these jelly beans, right? Um, so let's try to calculate how many jelly beans I need. I have 200 students, and I want each student to have 10 jelly beans. So that would be 10 jelly beans per student. Okay, so I multiply this out, and I end up with 2,000 jelly beans. Now, a lot of you were probably able to calculate this in your head. It never ceases to amaze me how your mind works. You just know that would be 2,000 jelly beans. And for some reason, when I talk about food and jelly beans, students are able to get that right away. But then when I put it in this format of conversion factors, students are like, what? So, um, you know, make it simple, keep it simple. And just try to think about it. What is per? 10 jelly beans per student. That per it's not like a cat purring. It's means divided by. Okay, so it would take me a long time to count out 2,000 jelly beans. And you probably wouldn't want me getting germs all over your jelly beans, right? Um, so it turns out that there are 400 jelly beans in 1 pound. Now let me specify. These are Jelly Belly jelly beans. I don't know if anybody has ever taken a tour of the Jelly Belly factory in Fairfield, California. My husband and I did a while back. And we would laugh because they had all these different drums where they would put more jelly beans and they would polish it, another sugar coating, or sugar polish. They put the jelly beans in with more sugar, and so it would make them shinier. But it was a ridiculous amount of sugar, not surprisingly. But anyways, so there are 400 Jelly Belly jelly beans in 1 pound. So let's say I bring in Jelly Bellies. So that means I'm going to take my 2,000 jelly beans. It would be a lot easier for me to weigh these out instead of counting them out. So 400 jelly beans in 1 pound. This is a conversion factor. That would look like this. 400 jelly beans in 1 pound. Okay, so you would put 400 jelly beans on the bottom and 1 pound on the top. And again, a lot of you probably did this in your head. You just know that it's 5 pounds of jelly beans. Okay, so it's a lot easier for me to weigh out 5 pounds of jelly beans than to count out 2,000 jelly beans. That would just be crazy. So we do the same type, or in chemistry, we carry out the same type of reasoning. Atoms are very difficult to count individually. So we frequently weigh elements knowing exactly how many atoms we should obtain. So if you look on your periodic table, what is the atomic weight listed for phosphorus? So if you look at phosphorus, that red number here, sorry, there's some shadows, 30.97376. So 30.97376. That is the atomic weight listed for phosphorus. Now, it is really annoying to keep track of all those numbers after the decimal. I always tell students to round to the hundredths except hydrogen. And that one goes to, hydrogen is 1.008. So what I'm going to do with phosphorus, I'm just going to round right here. So it would be 30.97. So 30.97. So what this number means, so this is the red number. This is the number that I've told you not to ever use, right? It's when we were working on isotopes, but now you can use it. So it turns out that there are 30.97 grams of phosphorus in 1 mole of phosphorus atoms. So 1 mole is kind of like our dozen. So 1 mole, and I have it written right down here, is defined as 6.022 times 10 to the 23rd units. So atoms, ions, molecules. So 30.97 grams equals 1 mole of phosphorus, which equals 6.022 times 10 to the 23rd phosphorus atoms. So 6.022 times 10 to the 23rd is a humongous number. It would take you forever to count all those atoms. So you wouldn't want to do that. Um, so that's why we can weigh it out on our balance. So if you weigh out 30.97 grams, which isn't that much, you will see that there are a ton of atoms in that. So it's just like those jelly beans. It's a lot easier for me to weigh out the jelly beans than count out the jelly beans. Okay, so Avogadro is the scientist who found out this number, the number of moles, and there's a mole day. So I'll put this, I always think this is funny. So mole day is October 23rd, so 10/23, and it starts at 6:02 a.m. So I always joke around with students on Mole Day. Can you eat a mole of donuts in celebration of Mole Day? And the answer would be no. That would be a lot of donuts. So, okay. So let's continue talking about applying this mole concept. So if I want to make 1 mole of sodium chloride, how many moles of sodium and chloride do I need? All right, so sodium chloride looks like this. Now, these subscripts, let me use highlight and circle so you can see this. There is not a number written here. And what that means is that's just 1 and 1. So to make 1 mole of sodium chloride, I would need 1 mole of sodium and 1 mole of chloride. Now if it was like Na2Cl, then I would need 2 moles of sodium and 1 mole of chloride. All right. So this brings us to molar mass. Molar mass is the mass of 1 mole of substance. Mass of 1 mole of substance. The units on this are grams per mole. Remember, you can write it like that, but I always tell my students to write it like this so you can see what's clearly in the denominator, numerator and the denominator. So what's on the top and what's on the bottom. It's not so easy to see when you write it like this. All right, so on the next page, I have you calculate the molar mass of some compounds. Now we're going to work through some of these together. So when I ask you to calculate the molar mass of potassium fluoride, what you're going to do is look up the atomic weight for potassium, and then you're going to look up the atomic weight for fluoride, and you're going to add them together. So potassium, you have 1 potassium, and you're going to look up the molar mass or the atomic weight listed for potassium, and that's 39.080983. So you're going to round that to the hundredths, so that's going to be 39.10. And then you're going to add that to the molar mass of fluoride. And fluoride, there's 1 fluoride, and that's 19.00. You add that together, and you get, so you add this on your calculator. Since we just have one of each, you can just add 39.10 plus 19.00. You don't have to put in the zeros, and you get 58.10. Now, what would the units on that be? The units would be grams per mole. Okay, so each compound is going to have a different molar mass because it's made up of different elements. So let's look at sugar here. You have carbon, hydrogen, and oxygen. And this time we don't have one of each. We have different numbers of each. This is where using your parentheses is going to be really important. So for carbon, I have 12 carbons, and carbon has an atomic weight of 12.01. And then I'm going to add that to hydrogen. Hydrogen, I have how many of those? I look at the subscript here, 22. So 22 times, oh, and hydrogen's the one I told you to go out to the thousands, so 1.008. And then oxygen, I have 11 oxygens, and they cost, no, they don't cost, but they come at an atomic weight of 16.00. I'm going to add these all together. And if I don't use parentheses, I'm going to come out with the incorrect answer. So be sure that when you're entering this in your calculator, you don't subtract, you end up using your parentheses. Okay. So I end up with 342.296. I'm going to round that to the hundredths. Sorry. Practice that on your own because it's very easy to enter it incorrectly. Okay, so sugar has a molar mass of 342.30 grams per mole. So that means that 1 mole of sugar is going to have a mass of 342.30, whereas 1 mole of potassium fluoride is going to have a molar mass of 58.1. So, if you weigh it out on the scale. All right, ammonium dichromate. I'm making you work on this one. I'm always trying to have you remember those pesky polyatomic ions because students don't think that they need to memorize their polyatomic ions. So I want you to try your hardest to come up with the formula of ammonium dichromate and the molar mass of ammonium dichromate. So hit pause. Try to, if you need to look up your polyatomic ions, I will allow that, but not on the exam. Okay, so hit pause and then come back. Okay, hopefully we got the same answer. So ammonium dichromate, remember that ammonium has a charge of +1, and dichromate is Cr2O7 2-. And you do the cross and drop, and you come up with this formula. I need to use the parentheses with ammonium because they have more than one polyatomic ion. And then I get dichromate here, just 1. So then I'm going to tally up everything. So I have 2 times 1, 2 nitrogen atoms. 2 times 4, 8 hydrogen atoms. And then I have 2 chromium atoms and then 7 oxygen atoms. I look up the atomic weights for all of these, multiply them by the appropriate multipliers, and I end up with 252.08 grams per mole. Okay, so that brings us to page 3. What are the units on molar mass? The units on molar mass are grams per mole. Molar mass can be used as a conversion factor. The number in molar mass is married to grams. No divorces here. So let's look at ammonium dichromate, for instance. Ammonium dichromate had a molar mass of 252.08 grams per 1 mole. What I mean when I say the number in molar mass is married to grams, this Sorry for this mirror. Always stays with grams. So 252.08 will stay with grams. It's never going to switch to moles. Okay, so let's say you have a starting quantity in grams. So I have, let's say I have 20 grams of ammonium dichromate. And I want to convert it to moles. I can use this as my conversion factor, that molar mass above. Now, in order to get grams to cancel out, I have grams here. I'm going to need to have grams in the denominator, okay? So that means I'm going to have to put 252.08 grams, 1 mole here. So you end up in moles. So on my calculator, 20 divided by 252.08, I end up with 0.0793. I would base my significant figures off of this. So I have 3 sig figs here, and I'll end up 0.793 moles, and that would be moles of ammonium dichromate. All right, now let's try the other way. If I had a starting quantity in moles, let's say I had 6.25 moles of ammonium dichromate, and I wanted to convert it to grams, I can go back to my molar mass conversion factor, and I can just plug it in. Now I need moles to be on the bottom in the denominator because moles are here. Okay, so 252 point, oops, sorry, I was not thinking. So I need moles to cancel there, so I'm just going to bring down my mole here. And that means the 252.08 is going to go right here. So moles will cancel, and I'll get into grams. So in my calculator, I'm going to do 6.25 times 252.08, and I end up with 1575.5 grams. Now, I'm going to use my starting quantity here. So I have 3 sig figs. So I need to round this to 3 sig figs. 3. All right, so I end up with 158 grams. Is that right? No. If I owed you $1,575 and I gave you $158, would you be happy with me? Absolutely not. But if I gave you $1,580, you would be happy. And the other way you could express this to clarify is to use good old scientific notation, 1.58 times 10 to the third grams. Okay, so you will see problems where you need to convert grams to moles or moles to grams. So let's look on the next page. So determine the number of moles in each of the quantities below. So I've given you grams. You're going to have to calculate the molar mass of all of these and then convert just like we did. And the same thing, we're going the other way here, determine the number of grams in the following. So you're going moles to grams. So with this first one, you're going grams to moles. This next one, you're going moles to grams. Notice that the compounds that I use in each 1 through 4 on the top and 1 through 4 on the bottom are the same. So you just need to calculate the molar mass once. What I want you to do now is to calculate the molar mass of sodium chloride, sulfuric acid, potassium permanganate, and magnesium nitrate. So hit pause, figure that out, and I'll put those molar masses there as well, and then you can go forward. Okay, so for sodium chloride, 58.44 grams per mole. Sulfuric acid, 98.08 grams per mole. Potassium permanganate, 158.04 grams per mole. Magnesium nitrate, 148.33 grams per mole. So now, what do you do? Well, for the first one, 25 grams over 1, you're going to use the molar mass as your conversion factor. So you're going to divide. So 25 divided by 58.44, you end up with 0.43 moles sodium chloride. Okay? So you're going to do that for the next three. And let me show you how to go from moles to grams. You start out with 2.5 moles over 1. And then you're going to multiply by the molar mass. So 2.5 times 58.44, you get 146.1 grams NaCl. But I'm going to make it 2 sig figs, so I end up with 150 grams, 150 grams of NaCl. Okay, so I want you to hit pause again and work through 2 through 4 on the top and the bottom. Okay, so for number 2, you're going to divide 125 by 98.08 and you get 1.27 moles, 3 sig figs there. Number 3, you get 0.639 moles of potassium permanganate. Number 4, you get 0.50 moles of magnesium nitrate. Number 1, we went over. Number 2, you get 49 grams of sulfuric acid. I get a lot of questions about should I write out the name of the compound, and I always say yes, just to avoid confusion, because when you're talking about grams and moles of something, it's grams and moles of what? Because every compound has a different molar mass. Okay, number 3, 269 grams of potassium permanganate, and number 4 is 37 grams of magnesium nitrate. All right, so work your homework problems on converting grams to moles and moles to grams and calculating molar mass. It's easy to make little nitpicky mistakes on this, so keep practicing. All right, so we have one more page left, and that will conclude this lecture. So sometimes the number of atoms is desired. So this is similar to when someone asks how many donuts are in 3 dozen. So if I have 3.2 moles of sodium chloride, somebody might want to know, well, how many units of sodium chloride is that? We use Avogadro's number. So remember that Avogadro's number, 1 mole, is 6.022 times 10 to the 23rd units. It could be atoms, it could be molecules, it could be ions. It just depends on what you're dealing with. So with this example here, I have 3.2 moles of sodium chloride. How many units of sodium chloride do I have? Well, I use this as the conversion factor. So I have 1 mole, 6.022 times 10 to the 23rd units. I'm going to calculate that out. The biggest part of difficulty with this is not setting it up, it's entering it into your calculator. So I'm going to put 3.2 times 6.022. And every calculator has a little different. Yeah. This one is really stealth. I don't even know if you can see it. See that little EE button? That's what you would press to do the 23rd, times 10 to the 23rd. What that means is times 10, the EE, and then, so I press second EE and 23rd. So some of you might have a double EE button here, like on my other calculator, it's just um, a button. You don't have to press second. Um, but if you have questions about where your exponent key is, please don't hesitate to ask me. I mean, that is the biggest part of the challenge. So the answer here is going to be 1.92. Sorry, we'll round this in a second. So it's going to be 1.92 times 10 to the 24th units. And I look at my sig figs. I'm going to go back to my starting quantity. So it would be 1.9 times 10 to the 24 units. Okay, so you just have to remember that 1 mole is 6.022 times 10 to the 23rd units. I'll just put. Okay, so you can get a question like this. How many atoms are in 0.58 grams? Notice I didn't ask for moles. I asked for atoms. That's how many. That's when you have to use Avogadro's number. But we're starting off in grams. So your roadmap would be grams. We can use Avogadro's number if we have moles. So you're going to have to go grams to moles, then moles to units. Okay, or in this case, it's going to be atoms. Okay, so you're going to do 0.58 grams over 1. Look up the atomic weight for carbon, 12.01 grams, 1 mole. So we cancel that out. And then 1 mole equals 6.022 times 10 to the 23rd atoms. All right, so 0.58 divided by 12.01 times 6.022, second E to the 23rd. You can't see that because of the glare. And we get 2.9 times 10 to the 22nd carbon atoms. Okay? Another type of question you could see is, what is the mass of 4.78 times 10 to the 24th molecules? Now, I didn't tell you what molecules they are. I would have to tell you what molecules. I'm going to say water molecules. Okay, so you're in molecules. You're going to have to go to moles. And then you can go to grams. So we're doing the reverse. So I'll write it here since there's not that much space. 4.78 times 10 to the 24th molecules over 1. 6.022 times 10 to the 23rd molecules. 1 mole. Really small. I need to leave more space in the future for these. And then the molar mass of water, you have 2 hydrogens and 1 oxygen. So that's going to be 2 times 1.008 plus 16. So you get 18.02 grams per mole. And I'm going to write my answer right here. So 4.78 times 10 to the 24th divided by 6.022 times 10 to the 23rd times 18.02. You get 143, and I can have 3 sig figs, 143 grams of water. Okay? So if you find that with any calculations involving Avogadro's number, that you're off by a power of 10, or by a power of 100, let me know because you're probably entering it into your calculator incorrectly. I think the most difficult aspect of these problems is entering it into your calculator. So make sure you're familiar with your calculator. And those little El Cheapo calculators, that they don't have this function. So you're going to need to use a scientific calculator. Otherwise, you won't get the correct answer. So be sure to practice on that for the exam. Okay, in the last part of this lecture, we're going to talk about chemical formulas as conversion factors. So how many wheels are on most cars? 4, right? So from that, we can generate a conversion factor. So one car has 4 wheels. Okay, you can do the same thing with chemical formulas. And, you know, students at this point, when we've learned how to calculate molar mass, we've learned how to go from grams to moles and moles to grams, and then we've learned how to use Avogadro's number. Students inevitably make this harder than it needs to be. It's very simple. How many wheels are on most cars? 4. One car has 4 wheels. Same thing goes with chemical formulas. So let's take CO2, for instance. So in 1 mole of CO2, you have 1 mole of carbon and 2 moles of oxygen. So now you can do the same thing for this formula here. So 1 mole of C10H14O, you have 10 moles of carbon, 14 moles of hydrogen, and 1 mole of oxygen. So this comes in handy when you get into higher level chemistries where um, you're going from grams to moles, and then you might be looking at a chemical reaction and going from moles of this to moles of that, and then you might be going into a formula and saying moles of this chemical formula to atoms of this. So it's very useful. For our course, we're just going to stop at generating a conversion factor from a chemical formula. But keep it in mind for future courses because it will come up, especially in your Chem 1 courses. So we covered a lot of material in this lecture. I want you to do the homework problems that pertain to these sections and practice them. Practice, 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 practice using your calculator. And I will see you. We have one more lecture for this unit, or for this week's lecture, and then I'll see you in class. So, all right, keep working hard. You guys are doing great.